Okay, thank you for coming. We got the real diehards in the room today. All right, so believe it or not, if all goes well today, I will finish all of the new material for this whole entire course, and then we'll spend the rest of our short time together reviewing. That's depending on how far we get today, but either way, we're getting close. Before I get into what I want to cover today, just a couple of reminders, mainly about, this Friday we have part of our final exam review, so just make sure that's outside of normal class time. That's going to be the 26th. So that's going to be part of the final exam review, roughly the middle part of it. And then we'll have parts of that as well in class on Wednesday, and then the final day of class. So that's going to be Friday at 1 p.m. here. All right, so same story as regular exam reviews. You have one more of those sessions this week in addition to the regular class meetings. And then also on Monday the 29th, we're going to finish the final exam review, but also that's when we have course evaluations. And I've gotten some questions about this. So this is the first year that the chemistry department has left the Stone Age and is doing online evaluations as opposed to paper ones. So some of you saw that it was already online and may have already done it if you're a real overachiever about those things. So if you did that, that's fine. Your evaluation will count. You don't need to do it again. But the evaluations are currently closed, and if you want to be able to do them and you haven't done them yet, you need to do them this day in class. They're going to open them back up during class. We're going to have people from the department here. Ideally, we want people to do them in class because we want the people that show up to class to do the evaluations, as that makes sense. But they were open previously. If you already did them, then you're all set. But you're going to want to come that day anyway because we're going to finish the final exam review. All right, so as always, if you have questions about those things, you're welcome to ask me anytime. And then as you get ready for the last two exams, whether you've taken the third one or not, I'll have office hours posted in Blackboard, so you're able to come whenever you need to. All right, so last time we started talking about vapor pressure, and we learned this equation, which we use in a couple example problems, which is that the useful form of the equation. I'll just review it here. We gave this last time, but the form of the equation we learned is that if you're comparing two vapor pressures at two different temperatures, so we said that vapor pressure increases with temperature, and this equation is sort of the quantitative relationship about that. So if you're comparing two vapor pressures, P1 and P2, one form of the equation that avoids any negative or minus signs out front of any of these terms is that you take the delta H vaporization over R. So this is enthalpy of vaporization, and then it's a difference of the reciprocals, 1 over T2 minus 1 over T1. So we did this last time, so I'm not going to go through all the details again, but this is the equation we learned. And what we're going to start talking about today is we're going to circle back to this in a little bit, but first let's get a more conceptual view of vapor pressure and some of the factors that influence it. So that equation dictates the relationship between temperature and vapor pressure. Increasing temperature corresponds with increasing vapor pressure. What are the relationships between intermolecular forces, IMFs, and vapor pressure? So this has an inverse relationship. So if you think about it, remember that vapor pressure deals with the process of molecules in the liquid phase escaping into the gas phase. So if you have stronger intermolecular forces, the molecules are going to be held in the liquid more tightly, and you'd expect less of them to escape in the gas phase. So the stronger the intermolecular forces you're going to result in lower vapor pressure. All right, and to write out what I just said, vapor pressure requires molecules to escape the surface. So if you have stronger intermolecular forces, you're going to have less molecules escaping the surface. All right, so that relationship is a new one involving intermolecular forces. We talked about a lot of other properties that IMFs are related to. This is a new one, and this time there's an inverse relationship. Stronger intermolecular forces correlates with lower vapor pressure. And then we also then have a relationship between intermolecular force and enthalpy of vaporization. So if you have stronger intermolecular forces, that means, again, the molecules are held more tightly in the liquid. You would have to think you would put more or less heat in to get those vaporized. So the stronger the forces, the more heat you have to put in to vaporize the liquid. So stronger IMFs correlates with larger enthalpies of vaporization. because you need more energy to break the IMFs. Because when we're going to vaporize a substance or boil it, which we're going to give the precise definition for here in a second, vaporization, again, requires us to break all of the intermolecular forces. And so if you have stronger intermolecular forces, you have to put more energy in to vaporize. And that should hopefully make sense conceptually as well. So these are some relationships involving that. And then what we're going to now introduce is a more precise definition of some of the phase changes. So we've kind of talked already about, boiling point. That's the temperature at which a substance boils. But what exactly does that mean in the context of vapor pressure? So the precise definition of boiling point is that it's the temperature at which the vapor pressure is equal to the atmospheric pressure. So we know that as we increase the temperature, we're going to increase the vapor pressure of the liquid. And once we get to the point where the vapor pressure is equal to the atmospheric pressure, that's what we call the boiling point. So it's the temperature at which the vapor pressure is equal to atmospheric pressure is the precise definition of boiling point. All right, so that's our definition. And then as we talked about, the enthalpy change that's associated with boiling or vaporization in more general is the enthalpy of vaporization. And that's always endothermic. And as we said, depends on the intermolecular forces in the substance. So it's enthalpy of vaporization is the associated enthalpy change, and we abbreviate that delta H VAP for vaporization. We also have a more precise definition of melting point, although this one ends up not being used as commonly, but it is the sort of exact definition. So we didn't really talk about this yet, but solids also have vapor pressures. So even though we talk about vapor pressure mostly in the context of liquid, if you have a block of ice, there's going to be some amount of vapor pressure above that ice as well. It's not nearly as large as it would be for the liquid phase, but every solid has a vapor pressure as well. And so the melting point is the temperature at which the vapor pressures of the solid and the liquid phases are equal. So again, both of these vapor pressures for the solid and the liquid depend on temperature. And once you get to the temperature where you have the same vapor pressure for the solid and the liquid, that's going to give you what's called the melting point, and that's the point at which the solid phase and liquid phase convert between each other or both exist. All right, so that's a more precise definition of melting point, but it's one that doesn't usually come up very much in context because we don't usually think about the vapor pressure of a solid, nor is it very important to usually think about it. All right, so that's what we mean for melting point. Really, the more common and easier definition of just it's the temperature at which a solid converts into a liquid. That works for us as well, but what that temperature really means is the temperature where you have equal vapor pressure for the solid and the liquid, and then those two are able to both exist simultaneously and convert between each other. So we didn't talk about this one yet, but melting also has an enthalpy change associated with it. So if you put again, if you're going to go from a solid to liquid, we have to put energy into the system, so it's also going to be endothermic. And what we call this is the enthalpy of fusion. Fusion is just a fancy word for melting. It doesn't really mean anything different. And it's also endothermic because you have to put energy into a substance to melt it. If you have a block of ice, you have to put it into a warmer environment for it to melt, as we know. So this is called enthalpy of fusion. It's the enthalpy change associated with melting. So it's in that direction. It's, again, the endothermic enthalpy change associated with melting 1 mole of a substance. So both of these enthalpy changes are usually per mole, and they're going to have different values. So each substance will have a characteristic enthalpy of fusion and a characteristic enthalpy of vaporization, which we'll talk about in more detail a little bit later today, and those are the enthalpy changes associated with each of those phase change processes. Now, when we say what is the normal melting point or boiling point, so both of these melting point and boiling point, they depend on the atmospheric pressure, and especially the boiling point. We said that the boiling point is the temperature at which vapor pressure is equal to atmospheric pressure. And so when we say normal melting point or normal boiling point, this is the situation where the surrounding or external pressure is 1 atmosphere. So for the normal boiling point then, we're talking about the boiling temperature at which the vapor pressure is equal to the atmospheric pressure, or 1 atmosphere. So that means for the normal boiling point, the vapor pressure will equal 1 atmosphere. So if we want to determine what's the normal boiling point of any substance, we just need to know at what temperature is the vapor pressure exactly equal to 1 atmosphere, and that's what we call the normal boiling point. So the boiling points that you're most familiar with, the one that you're likely already know, is water, which is 100 degrees Celsius. That's the boiling point of water at 1 atmosphere atmospheric pressure, which means that at 100 degrees Celsius, the vapor pressure of water is exactly 1 atmosphere also. So that's how those all relate to each other. And so what this then allows us to do with these more precise definitions in mind is we can do a slight variation using that equation that we learned last time. So let's say we have a liquid that has an enthalpy of vaporization of 35.5 kilojoules per mole and a normal boiling point of 122 degrees Celsius. What is this boiling point at the top of Pikes Peak, which is in Colorado, where the barometric pressure is 457 millimeters of mercury? All right, so we're going to use the information in this problem to calculate this boiling point at a different atmospheric pressure. So the boiling point depends on what the surrounding atmospheric pressure is, because it's the temperature at which the atmospheric pressure and the vapor pressure are equal to each other. So the first clue is that we have a normal boiling point of 1 atmosphere, which means that our initial pressure that we're considering is 1 atmosphere, so that's what we mean by normal boiling point. So at a pressure of 1 atmosphere, or when the vapor pressure is 1 atmosphere, or 760 torr, our temperature is 122 degrees Celsius. So that's what this first sentence means. The normal boiling point of 122 Celsius means that at 122 degrees Celsius, the vapor pressure, P1, as we're going to call it in that equation, is 760 torr. Remember that we have this equation that we reviewed earlier today, which relates vapor pressure and temperature. And so what we need to be able to solve this is a set of temperatures and pressures and how they relate to each other. So we're going to have this equation. And so our initial pressure, P1, is going to be this atmospheric pressure of 760. That's our normal boiling point pressure. And the normal boiling point is 122, which means that's the temperature that corresponds with that. And then we want to figure out what is the new boiling point, where the barometric pressure is 457 millimeters. So that's going to be our P2 term here, our second pressure that we're considering. And we just need to find what is T2, which is the temperature at which the vapor pressure is equal to 457 millimeters of mercury, which would then tell us the temperature at which that substance boils at that lower atmospheric pressure. So we're just going to start putting numbers in here. So P1 over P2, our initial pressure that we are comparing is atmospheric pressure 760. At the top of the mountain, the pressure drops to 457. And we can use whatever units we want because it's a ratio of 2 pressures, so the units divide out. And then on the right side of the equation, we have enthalpy of vaporization over R. As we talked about last time, enthalpy of vaporization needs to be converted to joules per mole because R is in joules as well. So it's going to be 35,500 joules per mole. And then the value of R that we want to use is 8.314 joules per K mole. And then our two temperatures need to be in Kelvin. So T2 is the temperature we're solving for. In other words, what is the temperature at which the vapor pressure is 457? And T1 is the initial temperature, 122 degrees Celsius, which in Kelvin is 395. We add 273 to that. All right, so these temperatures also need to be in Kelvin because they're absolute temperatures. So if we work this out numerically, we get on the left side the natural log of 760 over 457 is 0.5086. And that's equal to, if we distribute this out, I'm just going to work through the algebra real quick in case you want to follow this. We distribute out the right side of the equation. So we divide these two, which is 4,269.9, multiply it by 1 over T2, and then that number divided by 395, which is 10.1. So leaving units out, but just to quickly show you some of the intermediate steps for the algebra, what we solve for then is T2 is equal to 377 Kelvin, which is 104 degrees Celsius. So at the top of the mountain, where the atmospheric pressure is lower, the boiling point is also lower. And if you've ever closely read the instructions on, like let's say you get like a box of macaroni and cheese at the grocery store, trying to save on your grocery bill for that month, and you read the back of the instructions, what they at least used to have, I don't know if they do anymore because I have not made boxed macaroni and cheese in many years, but what they used to have on them was instructions where it said, at high altitude, cook it for 2 or 3 minutes longer. And that's not because time moves faster at the top of a mountain, but it's because the vapor pressure is lower, so the boiling point of water is lower at the top of a mountain. So if you're cooking food at a lower temperature, you need to cook it for a longer time to make sure it's actually cooked. And so this problem sort of shows that that's the case. If we go to the top of a mountain where the atmospheric pressure is lower, our boiling point for any liquid, any substance, would be expected to decrease because of that difference in pressure. All right, so any questions on vapor pressure? So we're going to now move on from it and talk about some other things related to that, but a little bit different. So any questions? Okay. So the next thing we're going to talk about is what's called a heating curve, which is sort of a multi-step process of taking a substance and heating it up through either phase changes or temperature increases or some combination of those two. So let's see what happens if we take a block of ice, which is initially at minus 20 degrees Celsius. So on the y-axis here we have temperature, and on the x-axis we have the amount of heat that we've added. And we're not going to, again, this graph is not like terribly important for us when we're doing problems of this type, but just to sort of help us understand, what happens to this block of ice as we add heat to it. So we're going to take a block of ice and we're going to either just, set it on the table, or maybe if we just put it in like in a pan on a stove and just slowly heat it, what sort of happens to that ice? So initially, if the ice is at minus 20 degrees Celsius, if we add heat to the substance, as we learned about back in Chapter 7, if you add heat to something, the temperature increases. So it's going to go from minus 20 degrees Celsius, where it's ice. So in this first segment here, we just have pure ice, solid water, and it's going to heat up. And then what happens at 0 degrees Celsius? Well, 0 degrees Celsius that's the melting point for water. So when it gets to 0 degrees Celsius, the heat that we're putting into it is going to cause it to melt and go from ice to water, solid to liquid. So at that temperature, for some period of time, it's going to be constant. So as the ice melts, the temperature remains constant. During any phase change, the temperature is constant. And we just have a mixture now of ice and water at 0 degrees Celsius until we've converted all of the ice into water, until we've converted all of the solid into liquid. And then once we have liquid water, what we know will then happen is when you have liquid water and you start heating it up, as we know from MC delta T, the heat equation that we learned a couple of chapters ago, as you add heat to liquid water, the temperature is also going to increase. And so we're going to add heat to the liquid water until it gets to 100 degrees Celsius, which is the next phase change. All right, so this is going to be liquid water. At that temperature range, we're heating it up and increasing the temperature. And then once it gets to 100 degrees Celsius, that's where our next phase change occurs. And at that temperature, 100 degrees Celsius, we're going to convert it into vapor, water vapor, what we call steam. So again, during the phase change, during the process when we're converting liquid water to steam, or liquid to vapor more generally, we're going to have no temperature change as that process occurs as we put heat into it. And then finally, once we have the water vapor, the steam, if we continue to add heat to that will continue to increase in temperature as well. So the gas phase water will also have some sort of a heat capacity associated with it, and as we add heat to it, it's going to increase its temperature as well. Okay, so steam does not necessarily have to be exactly 100 degrees Celsius. It can go higher than that if we continue to add heat to it. All right, so that's sort of what a heating curve looks like, and it shows that as we go through phase changes, the temperature remains constant. As we add heat to a single phase of matter, either the liquid, solid, or gas phases that we're showing here, the temperature will steadily increase. And as you should likely be aware from what we talked about in Chapter 4, the slope of each of these segments, which I did not really try to draw particularly accurate here, they all look kind of similar as it turns out as I've drawn them, but the slope of each of these segments is related to the heat capacity of the substance, which will not usually be the same for all states of matter. So you're going to have a heat capacity associated with the solid, in this case ice, a heat capacity associated with liquid water, which is that familiar 4.184 number that we learned in Chapter 7. And then you'll have another heat capacity associated with gas phase water or steam, which is some different number. So all three phases are going to have different heat capacities that are associated with each of these transitions here. And then the amount that we need to do the phase changes is related to the phase change enthalpy. All right, so let's put all that together numerically then with this type of problem here. So this is exactly the process I talked about last time, just in numbers now. So we want to know how much heat is absorbed if we take 5 grams of ice, initially at minus 20 degrees Celsius, and we heat it until it reaches the gas phase and a temperature of 140 degrees Celsius. So this is really the most comprehensive type of these heating curve problems I can do, because it includes all three phase changes as well as all three phases, both phase changes and all three phases of matter. And so what we're going to again do is think about this in individual phases. So the first phase is going to be, we're going to warm the ice from where it starts, which is minus 20 degrees Celsius, to the first phase change temperature. Now the only phase change temperatures you guys need to memorize are those of water, which are 0 degrees and 100 degrees, fairly easy and should be already familiar to you. So we're going to warm this from the starting temperature to the temperature at which the first phase change occurs, 20 degrees Celsius. And so within a single phase of matter, as we learned in Chapter 7, the amount of heat associated with that is mc delta T. Now the difference here is that we now have to make sure we use the correct heat capacity, because it will be different for the solid, the liquid, and the gas. So for this first phase, we have solid water, so we need to use the heat capacity of solid water multiplied by delta T. So we have 5 grams of ice. The heat capacity for solid water is given here as 2.09. So again, that's about half the amount for liquid water. That's just coincidence. There's no rule about that. But the solid phase heat capacity for water is 2.09, which is different than the liquid number that we're already familiar with. So that's the heat capacity we're going to use for this segment. And then the change in temperature, we're going from minus 20 to 0, so it's a delta T of plus 20 degrees Celsius or 20 Kelvin. So that comes out to 209 joules. Now, I don't think I specified in this problem, but we're going to end up calculating this in the end in kilojoules, so this is 0.209 kilojoules. All right, again, we would specify the units in the problem, but this is going to be 209 joules or 0.209 kilojoules for the first step, which is warming up the ice from minus 20 degrees to 0. That's just mc delta T. The second, what I'm going to do? I'm going to call these step 1, step 2, and step 3, because phase is kind of confusing because we're talking about phase changes, so let's call it step 1. Step 2 is going to be, once we're at 0 degrees Celsius, we're going to melt the ice. So once we get to that phase change temperature, we're going to melt the ice to liquid water. And for any phase change process, we learned about delta H's before, how we have, and here we're giving you the delta H of fusion is 6.02 kilojoules per mole. So if this is how much heat it takes to melt 1 mole of ice, we can figure out how much heat it takes to melt 5 grams of ice by considering how many moles this is and multiplying it by the phase change enthalpy. So to melt the ice is going to be the moles, in this case of the water, or the ice, multiplied by the enthalpy of fusion. All right? So melting, the enthalpy change is enthalpy of fusion. If we take the moles of substance, multiply it by the enthalpy of fusion, that's going to give us how much heat is required to melt that much of the substance. All right, so if we convert to moles, for this problem we have 5 grams, and the mole conversions are the same for any phase of matter, because there's always 5 grams of the same substance, and we just divide by the molar mass to get number of moles. All right, so what we should get is 0.278. So that's how many moles of water we're considering, and then so for the phase changes, we're going to use the moles, 0.278 moles, multiplied by the enthalpy of fusion, which is 6.02 kilojoules per mole. So what we get for that is 1.67 kilojoules. So that's how much heat is required to melt the ice. So that's the second step in this whole long process. Once we're at 0 degrees Celsius, we've converted it with wet 1.67 kilojoules of heat. We've converted all of the ice into liquid water. So then our third step is going to be to warm the water up until the next phase change. So we're going to warm the liquid water from 0 degrees Celsius, which is the temperature at which it melts, to the next phase change temperature, which is 100 degrees Celsius. So if this was anything other than water, we'd have to tell you what these phase change temperatures are to know what temperature range to use. Because again, water is the only one you really have to know what those numbers are. So in this case, we're going to go until 100 degrees Celsius. That's the boiling point of water. That's the temperature at which the next phase change will occur. And so again, if we're in a single phase of matter here, liquid water, we're just going to use mc delta T. This time we're going to use the heat capacity of the liquid, because we're at liquid water now. So we still have 5 grams of water. The heat capacity for liquid water is the familiar number 4.184. And the temperature change is 0 to 100, which is plus 100 Celsius or 100 Kelvin as a temperature difference. So this is 2,090 joules, which is 2.09 kilojoules. All right. So that's step 3, and then step 4. Once we reach 100 degrees Celsius is when we boil the water. So we're going to do going from liquid to gas phase water, and the associated enthalpy change for that is vaporization. So at 100 degrees Celsius, we're going to vaporize or boil the water. So again, Q is equal to the moles of the substance times the associated phase change enthalpy, which for this case is vaporization at 100 degrees Celsius. So we calculated there's 0.278 moles of the substance, and the enthalpy of vaporization is 40.7 kilojoules per mole. So the product of those two gives us the amount of heat necessary to vaporize the substance, which is 11.3 kilojoules. And I should have left more space because as usual I'm out. And then finally the last step we've gotten, so this is again, now we're in the vapor phase. The last step is to warm the steam, the vapor. From the phase change temperature of 100 degrees, and as we're told in the problem, we're going all the way up to 140 degrees. So this is the last step, is to warm that vapor to 140 degrees Celsius. And so this step here is going to be MC delta T as well. So the mass of water, heat capacity now of the gas phase water times delta T. So we still have 5 grams of water, and we have to make sure we use the right heat capacity. So for the gas phase here, heat capacity is similar to the solid, which is 2 joules per gram Kelvin. So we have to make sure we use the correct heat capacity for each stage. And then the delta T, we're going from 100 degrees to 140, so that's 40, a change of 40. So that step is going to be 400 joules, which is 0.4 kilojoules. And then finally, the total heat, after we have all 5 steps calculated individually, is just going to be to add these together. So we have 0.2909 kilojoules from the first step, which was warming up the ice. We have a 1.67 kilojoules that we calculated for melting the ice. We had 2.09 kilojoules for warming the liquid water. And then we had 11.3 kilojoules for vaporization. And then the last step was 0.4 kilojoules. So 5 steps here. We have to add them all together to get the total amount of heat, which is 15.7 kilojoules. All right, so I apologize for the mess, but I meant to leave an extra page here to do this. All right, so we get 15.7 kilojoules, total amount of heat to go through all 5 of these steps. As you see, most of that comes from vaporization, and that's not uncommon because, as we talked about, to vaporize a substance, you have to break all of the intermolecular forces. So we notice that the enthalpy of vaporization for water is much higher than the enthalpy of fusion, because to melt the substance, you just need to break some of the intermolecular forces. To vaporize it, you have to break all of them. So we see most of the heat comes from vaporization, but the sum of all of them comes out to 15.7. All right, we'll do one other example of this type. So here we have 0.333 moles of gaseous ethanol at 300 degrees Celsius in 1 atmosphere, and we cool it to liquid ethanol at 25 degrees Celsius. We want to know what is the total heat involved in this process. All right. So very similar type of situation. I'm missing a page. All right, I'll have to wing it. Oh, good. There's a calculator here I can use. All right. Okay. It's one that I'm not familiar with, but I'll try. All right, so we're going to take, again, we have a few steps to consider. So we're starting in the gas phase at 300 degrees Celsius. So the first step is going to be cool the vapor, or the gas, from 300 degrees Celsius to the first phase change temperature. Now this is a different substance, ethanol, so it's not going to be 100 degrees Celsius. It's going to be the boiling point where that's going to condense into the liquid. So remember, the boiling point is the temperature at which either the liquid will convert into gas or vice versa. So we're going to condense from 300 degrees Celsius to 78.5 degrees Celsius. We're going to cool that vapor. So the Q in this process is going to be MC delta T. And this is we have 0.333 moles, so we need the mass of this. Oh gosh, this is a terrible problem. I'm going to skip this. I'll put this in the notes, but there's just too much here to do. I don't want to go through it. I want to make sure we get through everything today. All right, so I'll write it out in abstract, and I'll fill in the numbers later because I don't have them in front of me. I don't want to spend a lot of time calculating them. So we're going to do MC delta T for this first stage, which is the gas. We have to calculate the mass, and then step 2 is going to be we're going to condense the vapor. Now remember, in this case we're condensing, so boiling is going to be, we have enthalpy of fusion here and enthalpy of vaporization. The enthalpy of vaporization is 40.5 kilojoules per mole. In this step here it's going to be the moles multiplied by the negative of the enthalpy of vaporization, because we're going in the opposite direction. So remember that we talked about the difference between the relationship between vaporization and condensation. They're opposite processes, so the delta H has a minus sign. So all of these terms should have negative Q's associated with them because it's going to be, we're cooling it in this case from a higher temperature to a lower temperature. So this is going to be a negative delta T for this one. So this term is going to have a negative value. And this time we have to take the negative of the vaporization enthalpy because we're condensing. All right, so that's going to be the second step, which I'll fill in the numbers afterwards, as I said. And then the third step here, once we're in the liquid phase, we're going to cool the liquid from the boiling point, which is 78.5 degrees Celsius, to the final temperature, which is 25 degrees Celsius. And again, this step here is going to be MC delta T. This time we have to use the heat capacity of the liquid times delta T. Again, a negative delta T. So all three of these terms will have negative numbers. I'll fill those in afterwards so you can see what those are, but I encourage you to try to get those on your own. So again, the key difference here is that because we're condensing and not vaporizing, we have to use the negative of the enthalpy of vaporization because we're flipping the direction of the process that we're doing. All right, so the last topic related to these heating curves and these processes of heating and cooling substances and phase changes is what's called superheating and supercooling, which again I think seem to be missing pages here. This is bad. All right, so let's just try to wing it again. All right, so supercooling is going to be the process of cooling a liquid below its All right, so there are some situations where we can cool a liquid and it'll go below the freezing point without actually converting into a solid. All right, so this is what we call a supercooled liquid. So we've cooled it below the freezing point, but it doesn't actually freeze. And then the question is, why does this happen? Why doesn't it just freeze when it gets to the, to that right temperature? The reason that it occurs is because it takes some period of time for the molecules to organize and solidify. All right, so even though we're at the right temperature for that to happen, we got to the freezing point, it doesn't happen immediately. So if you waited long enough, if you waited forever, on some infinite time scale, eventually it would freeze. But for some period of time, it exists as a liquid even though it's below the freezing point because the molecules just haven't had enough time to organize themselves. So that part's not really easily predictable when that happens or how long it takes to happen. All that stuff is very complicated. We're not going to talk about the details of it. But we just want you to be aware of the possibility of what's called supercooling. And you'll learn also in Chem 2 that you can formally supercool a liquid when it has stuff dissolved in it. So that's another process, that you'll talk about in the second substance, but in the second semester of this course. But even for pure substances, that sometimes occurs where you go below the freezing point and it still remains as a liquid for some period of time. And that's actually also important in a lot of biological processes. So my aforementioned identical twin brother studies supercooling in insects. So basically, how are insects able to survive these really low temperatures sometimes in some environments is because they're able to supercool the liquid inside of their bodies. And so this supercooling process also has some pretty important biological implications as well. But we just want you to know the definition of it. And then superheating, as the name implies, it's also dealing with a liquid. In this case, a liquid is heated above its boiling point, but it doesn't. But without it actually, without boiling occurring. So this would be if we took water. In some situations, again, it's very situation dependent. It doesn't always happen, but in some situations, we could heat water up above its boiling point, but we would still have the water as a liquid and not see the bubbles coming off the surface as you would expect when it boils. So that would be considered a superheated liquid, one that goes above the boiling point. This one is even more complicated for why it occurs, but basically you have either uneven heating of the liquid, so it might be an average temperature of 100 degrees Celsius, but you have pockets of warmer and cooler regions. You don't have enough higher temperature molecules, hot molecules together to form a vapor bubble and actually escape. So you have uneven heating. Or you have sometimes surface tension can give rise to this, where you formed, vapor bubbles inside of the liquid, but they don't have enough energy to escape the surface tension, and so they kind of stay in there. So we're not going to again talk about the real physical origin of this. It's a very complicated process, very complicated theories that you need to explain superheating and supercooling. We just want you to know the definitions of what they are and realize that even though we have these well-defined phase change temperatures for every substance, just because you go to that temperature doesn't mean it's going to immediately change its phase. It could exist at a lower temperature than its freezing point as a liquid, or at a higher temperature than its boiling point and still stay as a liquid, at least for some period of time. And that's what we mean by superheating and supercooling. All right, so any questions on the last couple things we've covered? All right, so the very last thing we're going to cover in this course are phase diagrams. All right, so let's give some general information about them. So what phase diagrams are, the two axes are going to be temperature and pressure. So we've talked a lot already about how the temperature of a substance influences what phase of matter it's observed at. We said we had the melting temperature where it goes from solid to liquid. We have the boiling temperature where it goes from liquid to gas. So temperature obviously is important for determining the phase of matter for a substance. Pressure is always also important. We saw that a little bit when we defined what boiling point really means, which is that depending on what the atmospheric pressure is, you're going to have different temperatures at which the substance boils. So temperature and pressure are the two major factors that influence what phase of matter a certain substance will exist at. And so what a phase diagram is a diagram that has those two on the axes. So it's going to have pressure on the y-axis and temperature on the x-axis. You could, in theory, reverse these and it would still give you the same information. So it's not that it has to be this way, but this is just conventionally how it's done. It's a temperature-pressure diagram, and you're going to have a specific diagram for each substance. So each substance is going to have its own phase diagram. And it's going to show the conditions, again in temperature and pressure, under which it exists in different phases. So this allows you to predict at any given temperature and pressure whether it's going to be a solid, liquid, or a gas. And there's also a lot of other information that can come out of a phase diagram as well, as we'll go through. So that's sort of the main point of a phase diagram, is you can predict at a certain temperature and pressure whether it's going to be solid, liquid, or gas. So the axes, again, are going to be pressure and temperature, as I already mentioned. Y-axis is going to be pressure. And the x-axis is going to be temperature. And in a typical phase diagram, you're going to have three regions, at least the most simple ones are going to have three regions, which correspond to the three major states of matter, solid, liquid, and gas. but sometimes, as we'll see in a couple examples, multiple solid phases are present. I think the first example I'll show you, which should already make sense now, is that if we have the phase diagram for carbon, we have both graphite and diamond, which are two solid forms of carbon. So that part of the diagram would actually be divided into a region for graphite, a region for diamond. So in many cases, and this is true especially for metals, which we're not going to really talk about a lot in the context of phase diagrams, but for many different substances, you have multiple regions on the phase diagram, which correspond to different solid phases that usually have different crystal structures. So when we talked about the crystal structures of metals as being, cubic, hexagonal, there's a lot of other ones we didn't mention, it will be the same metal existing in two different structures, potentially at different temperatures and pressures. So that's a possibility as well that we'll see in a couple of our examples today. So again, why are they useful? So in addition to telling us whether something is going to exist as a solid, liquid, or gas at a certain temperature and pressure, we can use them to predict when phase changes will occur, what temperatures and pressures. We can use these to graphically predict vapor pressure as a function of temperature. So we have an equation for that we introduced, but if you have this phase diagram, you can look at the graph and also predict the vapor pressure at a certain temperature. So you can predict vapor pressures and many other properties related to phase changes. And these also cover a wide range of conditions. So, phase diagrams are known for temperatures way beyond where we normally exist. So, we're talking for many substances, we have phase diagrams that go to, thousands and thousands of degrees Celsius, as well as really high pressures. So really a wide range of conditions that we can consider and understand the, physical state behavior of that substance under those conditions for whatever reason we need to do that in. So phase diagrams also have some practical applications as well. So for certain important materials that we use in our everyday lives, you have to use the phase diagram to basically predict what temperatures and pressures I have to go to prepare this material. And so even in a sort of an industry standpoint, they're important to consider as well. All right, so let's talk about the phase diagram for water. This is the first one we'll mention. And so we have, as I said, three regions in the phase diagram, and hopefully the regions where these things exist make a little bit of sense. So if we're at the very low temperature region on the left here, so again, the x-axis here is temperature increasing left to right, y-axis is pressure increasing bottom to top. So if we're at the lowest temperature and the highest pressures, what phase of matter do we think will exist? Solid, liquid, or gas? Lowest temperatures, highest pressures. If we cool water down to really cold temperatures, what does it form? A solid, a liquid, or a gas? Solid. Okay, good. So this region all the way on the left here is the solid region. It's going to be divided up by these lines, and we'll define the lines here in a little bit in a second. If we go to the highest possible temperatures all the way to the right here, and also low pressures, what phase of matter exists under those conditions? That'd be the gas, and then in the middle is going to be the liquid. So in a typical phase diagram that has three regions, solid, liquid, and gas, you'll have solid all the way to the left, liquid in the middle, gas all the way to the right. And they're divided up by these lines, and these lines are the different phase change lines. So the one that divides up the solid and the liquid here, if this lets me draw, is going to be this line here. So I'm going to highlight that in red. So that line divides the solids and the liquid region, and as the suggests, is called the solid-liquid line. And what this line allows us to do is to predict the melting point at different temperatures. So wherever there's this intersection between solid and liquid, wherever this border occurs, that's the temperature at which the substance melts. So it's going to allow us to predict the melting point at any different pressure that's given on this diagram. All right, so that's what that line tells us. And then we also have this line here between liquid and gas. We said that the conversion of liquid to gas is referred to as vaporization or boiling. And again, the temperature that corresponds to this borderline between liquid and gas is the boiling temperature at different pressures. So using this liquid gas line, which I've highlighted in green here, we can predict boiling points at any different pressure. All right, so if we wanted to predict the normal melting point of the substance, that would be the temperature at which the solid and liquid interconvert exactly at 1 atmosphere of pressure. So 760 millimeters is the temperature, the pressure associated with the normal melting point. So if we take where this intersects here, we see that's going to intersect there. We take that down to the x-axis, and that's going to be 0 degrees Celsius. So that point A here that I'm going to label with an A, that's our normal melting point. So if we extrapolate over from 1 atmosphere of pressure to the solid liquid line, that gives us the normal melting point. That's the conversion from solid to liquid at that temperature. And then if we keep going along the 1 atmosphere line, if we get to the liquid gas line, that temperature there is going to be the normal boiling point. So wherever we intersect the liquid gas line is going to tell us the temperature at which the liquid and the gas interconvert, which is the normal boiling point for that substance at 1 atmosphere of pressure. And we can see for water, the solid liquid line predicts a freezing or melting point right around 0 degrees Celsius, and when we go to this liquid gas line here at 1 atmosphere of pressure, we predict a normal boiling point of 100 degrees Celsius, which we already know is the temperature of the boiling point for water. So those are some of the basic things we can get from a phase diagram. Different regions where the substance exists in different states of matter, as well as phase change temperatures at any pressure we want to. We're going to give a few other definitions related to the phase diagram as well. So we're going to, same diagram, just going to make it a little bit smaller. So we have solid, we have liquid, and we have gas. All right, so one thing we can notice is that we have a negative slope for our solid liquid. It's not terribly obvious here, but you can see that this slope is negative. It goes sort of, if I was exaggerating, it goes like that, right? It's maybe not easy to see. If we go back to the big one, you can see that it's not perfectly vertical. It's a negative slope. And what does that tell us about the substance then? So if we start here, let's say in this region of the diagram, right next to that in the solid region, if we go up in pressure, at a constant pressure, at a constant temperature, as we increase the pressure, we're eventually going to cross over into the liquid. So when you have a negative slope between solid and liquid, as you increase the pressure, you will at some point convert from solid to liquid. So that's what the negative slope tells us. And what does that mean then about density? So as we increase the pressure, it converts from a solid to a liquid, because we're going to cross this phase change line if we keep the pressure constant. Again, a more exaggerated view would be as we go up, we eventually cross that line and go from solid to liquid. And what that tells us then is that the liquid is more dense than the solid. And the reason for that is if we take solid water and we start increasing the pressure, we're going to start putting pressure on it. We're going to pack the molecules closer and closer together, increasing the density. And then at some point, it's going to change to liquid water. So as we increase the density of the substance by increasing the pressure around it, eventually it's going to get to the liquid phase. That tells us that the liquid phase is more dense than the solid phase. And this is actually sort of a weird characteristic of water. This isn't the most common arrangement. Usually the solid is more dense than the liquid. Water is an interesting situation where that's opposite. And that's because in the crystal structure of water, you have these, you guys, well, maybe not in Houston, but if you've been to other parts of the country, you've seen snowflakes, which have this nice hexagonal shape. And the reason they have that nice hexagonal shape is because in crystalline water, in ice crystals, you have sort of hexagonal arrangements of the water molecules forming these hydrogen bonding sort of rings. And because you have those rings, you have some gaps in the structure, and the density is actually lower than in liquid water. So that's a weird feature of water that's not very common. But anytime you have a negative slope for the solid-liquid line, that tells us that the liquid is more dense than the solid. Some other important points on this diagram here. So this point here, which I think is labeled as an O, but I'll put an X next to it so you can see it clearly, this is the point where all three of those lines intersect. The solid-liquid line, the liquid-gas line, and the solid-gas line. So this is called the triple point of the substance, and this is the point at which the solid, liquid, and the gas all can exist simultaneously. It's the only point where that's true. So at that triple point, all three phases, solid, liquid, and gas, coexist. So you'd be able to have in the same sample, you'd be able to have ice, water, and water vapor all together, and that occurs at the triple point. And so basically under these conditions, the solid and liquid have the same vapor pressure. All right. So that's called the triple point of water. You also notice that below the triple point of water, we can no longer melt the substance from solid to liquid. If we go and increase the temperature below the triple point, we go straight from solid to gas. I'll talk about that in more detail on the next phase diagram that I'll show you. But that's what's called the triple point. It's the point where all three of those intersect with each other. And then the critical point here, we notice that the liquid gas line sort of just ends. It just sort of randomly comes to an end. That's called what's the critical point of the substance. I'm going to label that with a Y here. And so the critical point is the point at which the vapor can no longer be liquefied, or vice versa. So beyond this point, so if we go to higher temperatures or higher pressures beyond this point, so if we just that pressure and temperature, anything beyond that point, we don't have distinct liquid and gas phases anymore. This one's always harder for people to wrap their head around, but beyond this critical point, either higher temperature or higher pressure than that, the liquid and the gas are no longer distinguishable from each other. So they're indistinguishable, and they exist as what's called a supercritical fluid. So basically, beyond this point, the substance doesn't exist as a liquid or a gas. It's sort of almost like a new phase of matter that's where the two are indistinguishable. And beyond that point, so if again we go this way or this way, beyond that point, anything in this sort of direction there, moving beyond that point, no matter what temperature we heat it to, we're going to still have the same phase. We're not going to observe any vaporization anymore, any boiling process anymore beyond that point. I've never actually done any work with supercritical fluids, but there are some applications in chemistry where you use them. My understanding is that they're actually more like a liquid. They behave in a lot of sense like a liquid, but at that set of pressures, no matter what you increase the temperature to, it's not going to boil. It's going to stay in that same fluid state. So it's kind of in between a liquid and a gas, I guess you could think about it that way, but beyond the critical point, you no longer have separate liquid and gas phases. You just have one phase that we call supercritical fluid. All right, let's go to another example of a phase diagram, carbon dioxide, which should be subscripted, CO2. And this is going to have some similarities and also some differences from water. So the one key difference here is that we still have the same region, solid on the left, liquid in the middle, gas on the right. That's going to be probably the most important thing you have to be able to do with phase diagrams and homework and test questions. But one thing that we notice with carbon dioxide is that if we're at 1 atmosphere of pressure, this isn't bar, but bars and atmospheres are basically the same. So if we're at 1 atmosphere of pressure there, if we start at really low temperatures, we're going to have the solid phase, and we notice that as we work across and increase the temperature, we go straight from solid to gas. Okay, so we don't go through the liquid phase even at regular atmospheric pressure, in this case of 1 atmosphere. So this process is called sublimation. This is a new phase change that we haven't really talked about much, which is the process of converting a solid directly to a gas. So if we're at 1 atmosphere of pressure, CO2 sublimes, the sublimation temperature for CO2 is going to be this value here where we cross the solid gas line. So that's going to be minus 78.5 degrees Celsius. And this is probably something that you guys are familiar with from your everyday life. So this solid gas line is called the sublimation line, or tells us the sublimation temperature at a variety of pressures. And as you'll notice, that occurs below the critical point. So, or sorry, the triple point. So the triple point is here for this substance. Anywhere below the triple point, we're going to do sublimation directly from solid to gas. For CO2, the critical point, sorry, the triple point is above 1 atmosphere. Both of them are. The triple point is above 1 atmosphere for CO2. So if we're at regular atmospheric pressure for CO2, we go straight from solid to gas. And that you guys have seen in your everyday life if you've ever worked with dry ice. So dry ice is just solid CO2, which below minus 78.5 degrees Celsius exists as a solid. When you warm up solid CO2 dry ice, it goes straight to the gas phase. So I recommend not putting dry ice into a balloon and tying it, because that would, well, I guess the balloon would pop. That's not the world's most dangerous situation. But it does cause a pressure buildup, because as it goes from solid to gas, the pressure, the volume expands a lot and the pressure increases. So you want to be careful with that when working with dry ice. So that's what dry ice is. It's solid CO2 going directly from solid to gas without going through the liquid phase. We also notice that for CO2, this solid liquid line has now a positive slope. So that's also different from water. And that means that the solid in this case is more dense than the liquid, which is the more common situation. All right, and again, what that means is if we start in the liquid phase here, let's say, as we increase the pressure, we're going to be compressing the solid, making it more and more dense, putting the molecules closer and closer together. And as we do that at a constant pressure, if I can draw a straight line, at some point we're going to cross over into the solid phase. So again, that tells us as we increase the pressure, we go from liquid to solid, meaning that the solid is more dense than the liquid for CO2. All right, opposite of what we saw with water. So we can again predict relative densities of the phases based on the slopes of the line. Liquid will always be more dense than gas. You're never going to have a substance where the gas is more dense than the liquid. So this line will always have a positive slope. But in the solid liquid line can either be positive or negative depending on the relative densities of the solid and liquid phase. All right, so any questions on these phase diagrams before we move on to slightly more complex ones? Again, we're not going to get anything. There's only one that I just want to show you that's a little bit different. So any questions on these ones? All right, the last one I'll show you is, as I promised, the phase diagram for carbon, and this is one of the ones that has two different solid phases. So again, solid is all the way on the left, liquid in the middle, gas on the right. So we have gas down here for carbon in that region in the lower right. So anything in the lower right, that's going to be highest temperature, lowest pressure. That's going to be your gas phase. Highest temperature, but higher pressure is going to be liquid. And then over here we have two different solid phases. So the one that occurs at lower pressures is graphite. And the one that occurs at higher pressures is the form diamond that we talked about. So graphite is the most stable form of carbon. This diagram doesn't go all the way down to 1 atmosphere. 1 atmosphere would be about, I guess this axis here is probably about 10 to the 5th Pascal, which is around 1 atmosphere. So graphite is the stable form of carbon at 1 atmosphere. So that's what you expect it to exist at 1 atmosphere. But what we see for carbon is that if we take graphite and we pressurize it, we will eventually convert it into diamond. So if we take the graphite at a constant temperature and increase the pressure to really high values, we will convert it into a diamond. So that's one thing we can predict from this base diagram, which is true about carbon, is that at very high pressures, you have to go beyond like 10 to the 9 pascals, which is, about 10,000 atmospheres, a lot higher than you guys are used to in your everyday lives. But at those very high pressures, graphite converts to diamond. So it is possible to make synthetic diamonds this way, to take a carbon source, usually in the form of graphite, and just jack up the pressure until it goes into a diamond form. They don't look very nice, so people don't sell those as jewelry. The diamonds that you buy to propose to your significant other are going to be natural diamonds that are dug out of the ground and formed over very slow processes, but also at very high pressure, of course. But you can make synthetic diamonds just by increasing the pressure. And this is what we're not going to go any more complicated than this, but this is what a phase diagram looks like that has two different solid phases, in this case graphite and diamond. And like I said, a lot of metals have this same feature too, of having different solid states that exist depending on what temperature and pressure you're at. So what we're going to close with today is just sort of a slew of example problems to give you an idea of, now that we kind of know what a phase diagram is, what can we ask you about them on a homework question or a test? How deep do you guys need to know these things? What kind of analyses you have to be able to do? So generally speaking, we'll give you a pretty generic phase diagram, and at the very least, you need to be able to know which regions are solid, liquid, and gas. So that's what this is asking here is, what phases are present at point A? So I already heard someone say it. That's going to be the solid region all the way to the left, liquid in the middle, gas on the right. So if you can at least label the three regions, that's going to allow you to answer many of the questions we ask about which phases are present. So at point A, we're on the total left side of the diagram. We're not on any of the phase change lines. So we're only going to have solid present at this set of temperatures and pressures. Okay? This is just a made-up phase diagram. This doesn't correspond to any specific substance, I don't think, but we can use the features of a phase diagram to predict different aspects of it. All right, next one here, same diagram. We want to know which phases are present at point B. So if we go to point B, we again have to label the three phases to make sure we know which the different regions are. So solid, liquid, gas. So we'll notice here that, man, I'm like all disorganized today. We can do this one. Sorry, all right. Here we go. Point B is this one here. I'll make sure I stay on track. All right, so we're at point B here. We're on the borderline between the liquid and the gas phase. That means at that temperature and pressure, we're going to have both liquid and gas. So anytime you're on one of the phase change lines, both of those phases on either side of the line will exist at that set of temperatures and pressures. So at point B here, we have liquid and gas present, or liquid and vapor, same meaning, because we're in between the liquid and gas regions. This is at this particular pressure, this is where the substance would boil. That temperature corresponds to that. All right? So again, looking at the different parts of a phase diagram and knowing whether you're in either a single phase region or at a phase change region where you'd have two or more phases present is something we'll be able to ask you to do. So any questions on these two? Just reading the phases. All right, the next one goes a little bit in more detail. So we want to know which temperature and pressure are closest to the triple point. So again, labeling solid, liquid, and gas, just to keep those in mind. Remember, the triple point is the point where all of these three lines intersect each other. So the solid gas line, which is the sublimation line, the solid liquid line, and the liquid gas line, where those all three come together is called the triple point. In each phase diagram, at least for a simple substance like this, we'll only have one triple point present. And so that's the triple point. We just need to figure out what temperature and pressure this is. So this is just about reading a graph. So we extrapolate over to the x and y axes. We see that our temperature is between 100 and 150. I would estimate it as 120 Kelvin. And the pressure in this case, which we can more exactly read because it's right on the tick line, is 0.6 atmospheres. So at 0.6 atmospheres and 120 Kelvin, we would have, for this fictitious substance, all three states of matter present, solid, liquid, and gas, because that's where they all converge on each other. So the correct answer here would be choice A, 120 Kelvin for the temperature and 0.6 atmospheres for the pressure. All right, so we have to identify triple point as being, again, the one where all three come together. All right, so questions? All right, the next question deals with reading off phase change temperatures, so normal melting and boiling points for this substance. So the key word here is the normal melting and boiling point, which means that we're looking at a pressure of 1 atmosphere. So anytime we're asking about normal phase change temperatures, melting, boiling, sublimation, if that's appropriate, we're always talking about a pressure of 1 atmosphere. So what we need to do then to read off these is, again, think about which the different regions are, solid, liquid, and gas. We go at 1 atmosphere of pressure, and the first one we come to, once we get to the solid liquid line, that's going to be the normal melting point. So this point here, which I'll label as X, gives us the melting point. So we're always at 1 atmosphere of pressure. We extrapolate down to the x-axis to find the temperature that corresponds to, and that's going to be, this is in Kelvin, about 110 Kelvin. Did I do? Yeah, it's Kelvin for that. Let's do good. All right, so our melting point is about 110 Kelvin. So when we take 1 atmosphere of pressure, we go to where the solid liquid gas line intersects 1 atmosphere. We extrapolate to the x-axis to get a temperature of 100 Kelvin. So that's our normal melting point. And then if we continue on at 1 atmosphere of pressure, we go to where we intersect the liquid gas line. And this point here, which I'll label with a Y, is going to give us the boiling point of the substance. We're going to extrapolate down to the x-axis there, and we have to estimate this a little bit because it's not a very precise scale, but that's going to be around 220 Kelvin, somewhere between 200 and 250. All right, so that's the point where we go at 1 atmosphere, we intersect the liquid gas line, and wherever that temperature corresponds to is going to be the normal boiling point for that substance. So in this case, we don't have to use any calculations to do it. We can just read it straight off the diagram. So any questions on this? All right. So continuing to beat the dead horse. So what's the sublimation temperature for this substance at 0.4 atmospheres? So if we go at 0.4 atmospheres now, to find sublimation, we have to find out where we intersect the solid gas line. So that's going to be this line here, which is the borderline between the solid and the gas phases. If we're below the triple point, which is 0.6 atmospheres, anywhere below 0.6 atmospheres, we would sublime the substance, go straight from solid to liquid. So at 0.4 atmospheres, we go across, we intersect that line there, and that corresponds to a temperature of 100 Kelvin. All right. So if we define the correct pressure to use, which is 0.4 atmospheres, we can figure out what the sublimation temperature would be at that conditions of pressure. All right. And again, anywhere below the triple point pressure, so anywhere below 0.6 atmospheres, you would no longer have melting. You would have sublimation instead at those conditions. All right. Any questions? All right, I think just a few more to go through. All right, so this one is a little bit more of an elaborate word problem. So we might give you ones like this where we talk about different phase changes as we move through the diagram. So we start with the substance at 0.2 atmospheres and 100 Kelvin. So that's going to be about here, right at the, not there, read the diagram correctly. So we're starting at this point here, 0.2 atmospheres, 100 Kelvin, so that's our starting point. We're going to increase the pressure to 2 atmospheres while maintaining a constant temperature. Which of the following lists in the correct order the phases that will be encountered during this process? So again, we'll label the diagram with solid, liquid, and gas, make sure we know where each of those occur. And in this particular process, we're starting here, and we're going to keep the temperature the same, and we're just going to raise the pressure. So we're starting out in which phase of matter? The gas phase. That's our first phase. So I guess only one of the answers even works. So if you trust yourself, you could pick D as the answer and move on with your life. Let's verify that the rest of that answer is correct. That's the only one that even starts with gas. But if we start at a gas, we go up here, and eventually we're going to cross this line here. So what's the next phase of matter we're going to go to? Solid. So once we get to 0.4 atmospheres, which is this point there, we're going to cross over into the solid. And as we keep going up, because this is one of those substances that has a negative slope for the solid liquid line, eventually at that same temperature of 100 Kelvin, we're going to cross here. And what phase are we in now? So somewhere around 1.6 atmospheres, we're going to cross over and become a liquid. So just by increasing the pressure of this substance at this temperature, we can go through all 3 phases of matter. But the order is we start with a gas, we go to a solid, we go to a liquid. So choice D does work out. Gas, then solid, then liquid. Okay? Any questions on that one? All right. This one asks about relative densities, which we talked about already. So same situation. If we're at this temperature of 100 Kelvin, we see that as we increase the pressure, we go from solid to liquid, which means that liquid is going to be more dense than the solid. So we're increasing the pressure. We go solid to liquid, which means liquid is more dense than solid. And that's going to be true anytime our solid liquid line has a negative slope like we have here. All right, liquid more dense than solid. That's the situation we saw in water. That's the situation we see for this fake diagram here. All right. All right, last question. What is the vapor pressure of this at 250 Kelvin? So the nice thing is that if we go to any point where we're on along the liquid gas line, so we have solid, liquid, gas, anywhere along this line, if we just read off a temperature and pressure, that's going to give us the vapor pressure at that temperature. Because remember, this line tells us the temperature at which the substance boils. Boiling occurs when vapor pressure and atmospheric pressure are the same, so this line will also give us the vapor pressure of that substance. So if we go to 250 Kelvin, we extrapolate up to the liquid gas line there, and we extrapolate over to the x-axis to figure out what pressure that corresponds to. So that means the vapor pressure of this substance, it's going to be a little bit bigger than 1.2 atmospheres, maybe 1.25, 1.3 would be a good estimate, somewhere around there, as precise as we can be. So it's about 1.3 atmospheres. So again, we find the temperature that we're talking about, we go out to the liquid gas line, we figure out where it intersects, we extrapolate over the y-axis. So hopefully this shows you that there's a lot of information you can get from a phase diagram. I don't think the questions we'll ask in the test will be any more difficult than this, but there will be one on the final that expects you to interpret phase diagrams. So that takes us to the end of all Chem 1331 material. Everything from here on will be a review. So on Wednesday I'll start with reviewing some of what I think are the more difficult topics in this course, and then we'll go right into the final exam review, starting with the problems that are already posted in Blackboard. All right, so I'll see you guys on Wednesday.